Welcome to qnawire.
So in this video, we're going to talk about question 118 from chapter 20, which says, although nitrogen trifluoride, NF3, is a thermally stable compound, nitrogen triiodide, NI3, is known to be a highly explosive material. NI3 can be synthesized according to the equation Bn plus 3IF yields BF3 plus NI3. In part A, we're asked, what is the enthalpy of formation for solid Ni3 given the enthalpy of reaction and the enthalpies of formation for Bn, IF, and BF3? So how are we going to solve this? Well, we know that the enthalpy of reaction is equal to the enthalpy of formation of the products minus the enthalpy of formation of the reactants, each multiplied by their stoichiometric coefficients. So we have our delta H is equal to HF of BF3 plus HF of Ni3 minus 3 times HF of IF minus HF of Bn. So all we have to do is solve this equation for HF of Ni3, and then plug in all the numbers that we were given in the problem. So the equation we end up with is delta H minus HF of BF3 plus 3HF of IF plus HF of Bn. And then once we plug everything in, this evaluates to 287 kilojoules per mole. So that's the enthalpy of formation for Ni3. In part B, we have, it is reported that when the synthesis of Ni3 is conducted using 4 moles of IF for every 1 mole of Bn, one of the byproducts isolated is IF2 plus BF4 minus. What are the molecular geometries of the species in this byproduct? What are the hybridizations of the central atoms in each species in the byproduct? So let's start with our cation, with our IF2 plus. So we know that each of our halogens is going to bring 7 electrons. So that would give us 21 electrons from our 3 halogens. And then we have a +1 charge, so we have 1 fewer electrons than that. So we have 20 electrons total to work with. So if we just draw each of our fluorine atoms singly bonded to our iodine atom and then fill in the octet, then what we're left with is 4 electrons that we haven't used yet. And we can put those 4 electrons, those 2 lone pairs of electrons, on our central iodine atom. And so the Lewis structure that we end up with has 2 bonded atoms around our central atom and 2 lone pairs, which implies that we have a bent geometry. And the fact that we have 4 things surrounding our central atom, 2 bonded atoms plus 2 lone pairs equals 4, that means we have an sp3 hybridization. So what does this bent structure look like? It looks like a tetrahedron where 2 of the corners of the tetrahedron are lone electron pairs, and the other 2 corners of the tetrahedron are fluorine atoms, and that makes our bond angle 109.5 degrees. So what about our anion, which is BF4 minus? Well, we know that our boron is going to bring 3 electrons, and each of our fluorine atoms is going to bring 7 electrons, and because we have a -1 charge, we have 1 additional electron. So if we add all that together, we have 32 electrons to work with. So a good starting point would be to draw each of our fluorine atoms singly bonded to our central boron atom, and then fill in the octet on each of the fluorine atoms. And when we do that, we actually use up all 32 of our electrons. So that's our Lewis structure for BF4 minus. So this Lewis structure has 4 bonded atoms around our central atom and 0 lone pairs, which means we have a tetrahedral structure. And since 4 plus 0 equals 4, we only have 4 things around our central atom. This is sp3 hybridized as well, just like the cation. So what does this look like? It just looks like a tetrahedron with boron at the center, and each of the corners is a fluorine atom. And same as before, our bond angles are 109.5 degrees.